Okay, so yeah, good morning, everyone. This is Tom Ebergen's master's thesis defense. And without further ado, Tom, let's take it away.
All right. Thank you so much, Gabor. How is everyone? Good morning. Thank you all for being here today. As Gabor mentioned, this is my master's thesis defense on joint order optimization with almost no statistics. So let's take it away. First, we'll start with a general overview of query processing. Queries usually start out in a high-level query language, which is normally SQL, and then they're scanned, parsed, and validated to ensure the semantics and the syntax of the query are all valid. And then once the query string passes these checks, an internal representation of the query is created, and this is called a logical query plan, and this is usually in the internal structure of a tree. The query tree or the logical plan is then optimized and transformed, and then after the optimization process, it gets transformed into a physical query plan. The difference between a logical query plan and a physical query plan is that a logical query plan describes what should happen, while a physical query plan describes exactly how that should happen during the execution process. So the physical query plan is then passed to the execution engine, and then the execution engine produces your query result. Query optimizer here is in bold because that is specifically what I have been researching for the last 6 months. So diving a bit more into query optimizers, there's two types of optimization techniques that can be employed either together or independently. And these optimization techniques are specifically for logical query plans. There are also physical optimization techniques, but we won't be covering those in this presentation. So rule-based optimization is one technique where rules are applied to a set of operators that have certain characteristics. So the first example is filter pushdown, where if you have a filter operator in a query tree, you can push it down to just above the table scan operator, and then that avoids processing unnecessary tuples throughout the rest of your query tree. Another example of rule-based optimization is expression rewriting. So if you have a set of operators that can be reduced without needing any data, you can automatically reduce those in the query tree without having to evaluate it per tuple that you're processing. Another type of optimization is cost-based optimization. And in this type of optimization, you have multiple different possible optimizations that you can apply, but it's not certain which one is like the most optimal. And so in these cases, you estimate it using a cost function. One example of this is joint order optimization, and that is, again, more specifically what I've been researching for these last 6 months. So let's dive in a bit more into what joint order optimization is. First, I'll say that it's a very difficult problem. A joint order, there's n factorial possible joint orders that you can have given n relations or n tables that you're scanning from. So this is a very popular question in database systems and database research. So just as a general overview, I'll start with the three main components of joint order optimizing. You have a plan enumerator, a cardinality estimation, and a cost model. The enumeration algorithm can be quite complex, and so I won't cover that in detail in this presentation. But in summary, joins between sets of relations are enumerated. So after a dynamic programming table is initialized with base table information, the enumerator will first enumerate its first two sets of just base tables. So in this example, B and C, that gets passed to the cardinality estimator. And the cardinality estimator then can use any type of statistics or histograms to estimate the cardinality of a join between tables B and C. Passes the estimated cardinality to the cost model. Cost model can use the estimated cardinality plus other inputs. Those could be hardware inputs based off of where the memory for those tables specifically lives in memory, what the read speeds are. Potentially it's a distributed system and you got to read it from a different system across the planet. Those can all go in the cost model, and then the cost model updates the dynamic programming table with the cost of the specific join of B and C. And so then after that, the enumerator will enumerate the next set, in this case, A and B. Process is relatively the same. You get the cardinality estimator, it goes to the cost model, updates the dynamic programming table. Now here we get the enumeration of the set A with the set B and C. Pass it to the cardinality estimator, again, using statistics, histogram, has an estimated cardinality, passes it to the cost model. And in this case, it's important to note that the cost model then now factors the estimate of the cardinality between the set A and BC, but also the cost of the child join of B and C. So that's why you see a cost of 20,000 because it's the addition of the cardinality of the join between B and C, and then also the estimated cardinality of A with B and C. The last enumeration is then A and B with the set C. Again, goes to the cardinality estimator, has the same estimate, and now the cost model uses the cost of the child of A and B, and then you get a smaller cost. You should get a smaller cost of 10,500. And then that gets updated in the dynamic programming table for the input of the set A, B, and C. And it's very important to note that in this dynamic programming table, the entries are stored as like the sets of relations. And then the specific join order is stored via references in the dynamic programming table. So if you go to any entry in the dynamic programming table, that doesn't tell you the whole join order. You have to follow the references of the left and the right child node. And then that will eventually give you all of the references and the specific join order. So this should give you kind of an overview of how join order optimization works, what the problem is, and some of the challenges that can be involved. Now let's switch gears a bit here, talk about DuckDB. This is where I implemented my findings over the last 6 months. So general overview, DuckDB is an open source in-process database system for analytical queries developed here at CWI. It's popular among data scientists for its ease of use and its high performance. It regularly hits the front page of Hacker News whenever a new blog post is published, and it has over 100,000 monthly downloads. It has a vectorized execution engine as well, similar to what VectorWise had, and it collects minimal base table statistics now, being just a hyperlog estimate on 10% of every vector that is ingested. Okay, yeah. And then it can also run directly on Parquet and CSV files. And for those instances, those queries, no base table statistics are ingested. We only have access to the cardinality of these tables and potentially for Parquet files, minimum and maximum statistics. So now let's go into the DuckDB join order optimizer. And this was before I started working. So strengths, the dynamic programming algorithm for plan enumeration was very strong. It was state of the art. But sometimes because there are n factorial potential join plans, it would switch to a greedy enumeration algorithm. But one of the big weaknesses of the join order optimizer was that the cardinality estimator was very simple. So it would assume every join is a foreign key primary key join, and then it would just assume that the resulting cardinality of the join was the cardinality of the larger table. Another weakness on top of that is that table filters weren't estimated either. So if you apply a table filter on top of tables that are eventually joined, the effect of that filter isn't even calculated into the cost. So given these kind of what the DuckDB join order optimizer was, we can set some constraints for ourselves and a research question, or project goals, and that is to develop an accurate cardinality estimator using minimal to no base table statistics. We want something at least more accurate than just assuming the cardinality is the size of the larger table. We want to improve the DuckDB join order optimizer to select query plans with faster end-to-end execution times. So this means any overhead that we put into the optimizer, we want to justify that with faster end-to-end execution times. And then our third goal is to implement this and evaluate this, the new join order optimizer, and potentially ship it if possible. So put it into DuckDB so that people can actually see the effects. Awesome. Now let's move into the actual research. So starting with the cardinality estimator. The original concept for the new cardinality estimator was to incorporate the idea of selectivities and multiplicities with the assumption that every join is a foreign key primary key join. So when a foreign key primary key join happens, column values can be filtered out if they have no match, or they could be duplicated if they have multiple matches. So we define multiplicity and selectivity. Definition for multiplicity is the average frequency of all distinct values in a column. And the selectivity is the average probability that a domain value is in a specific column. And here we also have some mathematical definitions for these terms. So CDOM represents the current domain of a column A.W. TDOM represents the cardinality of the total domain of column A.W, and then card A is just the cardinality of table A. And then, so you can see on the right-hand side, we have two columns, A.W and B.X. If we assume a foreign key primary key relationship between the two, then they have the same total domains. If we move on, so we can define multiplicity and selectivity then using just the terms we defined, the current domain, the total domain, and the cardinality. And we can apply these definitions then to the columns that we have on the right. So multiplicity is the cardinality over the total domain. And you can see for the primary key column, the multiplicity is 1 because it's not allowed to have any duplicates. And this means that the cardinality is equal to the total domain for primary key columns. For foreign key columns like B.X on the right, the multiplicity can be greater than 1 because duplicates, of course, are allowed in foreign key columns. For the selectivity, we define it as the current domain over the total domain. And for primary key columns, again, selectivity is 1 because the primary key column defines the total domain. We've also in the multiplicity equation said that the cardinality is equal to the current domain. So if the current domain is the cardinality, then the total domain has to be the cardinality. So for A.W, the selectivity is 1, and then for B.X, the selectivity is 4/5. And you can see that because B.X is missing the yellow value. These definitions most basically only work under the independence assumption. So we are assuming that all values are uniformly distributed. This, of course, makes these equations susceptible to skew and correlation. Yeah, just mentioning that. Specifically, multiplicity is very susceptible to this. So using these, we can now define a cardinality estimation equation. So suppose we're given two tables A and B, and they have a joint condition A.W is equal to B.X. We want to know then the cardinality of A join B. So we take one tuple from A, the number of expected tuples in the join A-B where the tuples are equal to Z is just the selectivity of B.X times the multiplicity of B.X. Why? Well, the selectivity, we said that is the probability that a specific value is in the domain of that column. And the multiplicity is then the average frequency of all values. So we can extend this very easily, and we can just say, okay, the cardinality of A join B is in all tuples in A, the cardinality of A times the selectivity of B.X times the multiplicity of B.X. Using this, we can substitute in then our definitions for the selectivity and the multiplicity using our current domain and total domain terms. I'm going to get this very nice equation and reduction. So you can see that the current domain terms cancel each other out. And all we're left with now is the cardinality of the base tables. This is great. You don't need to keep track of a current domain. You have just the cardinalities of the base tables and the distinct count of the column that they're joining on. This is minimal statistics. This is exactly what our thesis goal was. And further reduce this equation and rewrite it to pull out the total domain term and label it now as a joint selectivity between two columns, where the joint selectivity is just 1 over the total domain of the columns that are being joined. This equation is very simple, similar to known joint estimation equations. I thought I can't be the first one to figure this out. It turns out it is in a couple of older papers, Leo and System R, but those papers don't go into how effective this equation can be. And also I develop it a little bit further in the case of no statistics. But first, this equation also only assumes there's one join filter connecting two tables. What if there are multiple? If we want to ship this to production, users are users. So sometimes there can be a lot of join filters. So in this case, we have to decide, do we want to apply all of the join selectivities. Which join selectivities do we want to apply specifically? Let's see. Well, in this example, I look at this and I see that these tables represent vertices, the edges represent join conditions, they have weights of join selectivities. I took graph theory courses in my bachelor's. I know what this looks like. We can build a minimum spanning tree. And then we just apply the join selectivities of the edges in the minimum spanning tree. And we can apply the product because the product is also a monotonic function. So that works when we try to discover our minimum spanning tree. Let's see. Yeah. I don't want to rush through this too fast. So this gives us our cardinality estimation equation. That's a lot of math, but we'll just take a little bit to read it. So we're given our set of relations. We're given our join conditions, which all have a weight of a join selectivity, or join conditions, which represent our edges, and they have a weight of the join selectivity. And again, every join condition joins two tables in our set of relations. So then our cardinality, our estimated cardinality of all the relations that were given is basically the cross product of all of the tables times all of the join selectivities in the minimum spanning tree that is created using the relations as vertices and the join conditions as edges. What's great is that, yeah, in the beginning of our thesis, there was a lot of talk about making sure that this estimation equation was associative and commutative. We went down a lot of dead ends for an estimation equation because we couldn't prove these properties. And now we have a cardinality estimation equation that's one big product, and it is the product using an input of a set of relations. So we're not storing anything anymore about a specific join order in this estimation equation, just the base table relations. So this fits very nicely into the dynamic programming algorithm that I showed you guys, the join order optimizer, because again, the entries in every single entry in the dynamic programming table is a set of relations. Awesome. So it looks like we're almost done, but we're still missing one more thing. And I want to know if anybody here can spot that. We think back to DuckDB, we think back to our thesis goals. It's not necessarily, right? DuckDB can query on base tables, but also on CSV and Parquet. And you guys can say it if you know it.
No statistics.
Right. What if we don't have statistics? Our minimum spanning tree assumes that we know the number of distinct values in a column. But what if we don't have that? What if we're querying directly on Parquet or CSV? Then we introduce equivalent sets. Equivalent sets are sets of column relations that are transitively joined. So in this slide, you can see we have 4 tables and we have 2 equivalent sets. A.1 and B.1 are an equivalent set, and B.3, C.4, and D.1 are an equivalent sets. Equivalent sets can help us determine the primary key column for joins, and therefore also the total domain. So remember, we assume that every join is a foreign key primary key join. So for all columns in an equivalent set, one of those columns must be a primary key. And then we say, okay, let's just loop through all of the columns in the equivalent set. The column with the minimal cardinality, we will then assume to be the primary key because it's not allowed to have any duplicates. Yeah, so now we can just use the same estimation equation. We have a total domain for all of our columns, and we can do it with no statistics. One more thing I want to talk about is selectivity estimation. So with statistics, selectivity estimation is really easy, or it's easier to do on base tables, specifically in the case of equality filters. So here you have region.rname is equal to Asia. If we know how many unique or distinct values are in the table, in the column region.rname, then we can predict how many tuples would be produced from the filter F1, which is just the cardinality over the number of distinct values. If we don't have statistics, we just use a very naive estimate of 20%. Let's move on to the cost model, which is also part of join order optimization. So we use the cost model from the paper, How Good Are Query Optimizers Really, which is just the addition of all of the intermediate cardinality counts. This is a very simple cost model, but in the paper, it was shown to be almost as good as very complex ones. What's nice about this cost model as well is that the cardinalities and the costs are distributive. So if the first joins that you apply, the cost of those joins end up applying to the later joins. That's very nice to see. I'm not putting the whole derivation on the slide. It will be in my thesis, but it's very nice to see that just theoretically, this cost model also avoids applying expensive joins first. Great, now we can go into the experiments. This is the fun stuff. I implemented all of this in DuckDB, I should mention, and ran some experiments. So the benchmarks that we tested it on are TPC-H at a scale factor of 10, which is about 10 gigabytes of data, the join order benchmark, and the join order benchmark on Parquet with that has no statistics. If you're not familiar with the TPC-H benchmark, it's a standard decision support benchmark. It's on synthetic data meant to model business-like data sets. There's not that many joins. And the join order benchmark is a real-world data set built on the IMDb data. It has skew and correlations, making finding efficient join ordering very difficult. Has between 3 and 16 joins per query with an average of 8. And it's about 3.1 gigabytes of data in CSV form. We compared our results with Postgres and SQL Server, and as well as explicit plans gathered from Simplicity Done Right paper, which was produced by the University of Dresden. They use very accurate selectivity estimates on base table filters, along with an upper bound on join estimated cardinalities for joins to find some very accurate and high quality join plans. DuckDB old is DuckDB without these query optimizer, join order optimizer improvements, and DuckDB TDOMs is DuckDB with the query optimizer improvements. For end-to-end execution results, all the tests were just run on this laptop, which is an Apple M1 Pro from last year, 32 gigabytes of memory. Yeah. So another note about the results, this talk will present normalized results. So intermediate cardinality counts are normalized to a baseline. So for some query, if a baseline produces an intermediate cardinality count of 100, and another system then produces an intermediate cardinality count of 200, the results are 1 and 2 respectively. So now we can get into the results for TPC-H. These are the 4 queries that stand out the most. As you can see with query 5, and we improved by about 5 times. Query 8 is about 10 times. Query 9, about 20, over 20. And query 21, about 3 times. Some pretty good results. These are just for intermediate cardinality count. So this means that when we run the query plan, the amount of intermediate tuples processed is recorded, and then that is normalized to the baseline, which in this case was Postgres. I forgot to mention. So that's why Postgres has 1 each time. And then you could see DuckDB old produced 5 times as much as Postgres. If we look at now end-to-end execution times, these are for the same queries. You can see that we improved for each one of those queries. These execution times are normalized to DuckDB old. So for query 5, we're looking now like we are 95%. So 5% better than DuckDB old. For query 8, we're about 20% better. Query 9, 5 times better. That's huge. Yeah, and then query 20, wow, 20% better. Now we're moving on to, so query 9 is the most challenging join order in the TPC-H benchmark with 6 joins. And so the next results that we're going to be looking at are join order benchmark results, and those have between 3 and 16 joins per query, again with an average of 8. It's much harder to find accurate join plans for these queries. Awesome. So again, intermediate cardinality counts. Here's a table. The first thing I want to bring up is DuckDB old. If you look at the max and the average, you can see that DuckDB old was about an order of magnitude off from state-of-the-art systems. If you look at DuckDB TDOMs now for the max, average, and median, we are now, or DuckDB TDOMs is in the ballpark of the state-of-the-art systems, that is a big result. Yes, so that is an improvement of 98% for the max, 95% for the average, and 92% for the median. And you can see for the median, we're right there with the state-of-the-art systems. For the average, we're still a bit high, and that means that we have a couple of plans that are producing much higher intermediate cardinality counts. But again, we don't have good table selectivity estimates. So there's reasons for that. If we look at execution times, note that the y-axis on the right is a log scale. But again, we see improvements in the max, average, and the median. So the max improved by about 40%, the median by about 25%, or the average about 25%, excuse me, and the median about 10%. Moving on to joint order benchmark on just Parquet files. So in these cases, we don't have any table statistics, and we just assume the cardinality of all of the columns that are eventually joined in each of the queries. So again, DuckDB old is the same if you run it on base tables or on Parquet files. And again, almost an order of magnitude off from the state-of-the-art systems. But if we look at now DuckDB TDOMs on Parquet files, we see an improvement of 78% for the maximum, 65% for the average, and 87% for the median. And so again, the median, this is great. This shows us that 50% of the time, DuckDB on just Parquet files is producing 1.6 times the amount of intermediate tuples as state-of-the-art systems. These state-of-the-art systems, which do collect statistics and which do collect statistics on correlation and skew and take much longer to ingest all that data. Awesome. Looking at end-to-end execution times, again, we see improvements. So for the max, we see an improvement of 68%, 18% for the average, and for the median, we see an improvement of 1%. These, I've said that on the last slide that, there's big improvements for these intermediate cardinality counts. But then now if we look at the end-to-end execution times, we don't see as big of an improvement. And there is a reason for that. That's because our optimizer is taking much longer. So before we had this dynamic programming, plan enumerator to enumerate sets of possible joins, but it would only enumerate about 2,000 pairs. Now it enumerates 10,000 pairs. And on top of that, every time we estimate a cardinality, we do have to find the minimum spanning tree. And that is still using, the full algorithm, and there are ways to optimize that. But right now hasn't been implemented yet. But as you can see, as the number of relations goes up, our optimizer takes so much longer than it used to, or much longer. Up to, I think, around 9 relations, it's about 10 times as long. Great. All right. So we developed a cardinality estimator using minimal statistics. While we didn't test its accuracy, the improvement in the quality of join plans is an indicator that it has a lot of potential. The quality of the selected plans improved considerably, comparing intermediate cardinality counts and end-to-end execution times. And again, while the optimizer time has increased, as I just showed you, the end-to-end execution time went down. So this increase in optimizer time is justifiable, but again, it's an area that we can still improve on. So we go back now to our conclusion. This is just a copy of the thesis goals. We developed an accurate cardinality estimator with minimal to no base table statistics, improved the DuckDB join order optimizer to select query plans with faster end-to-end execution times. And we have implemented it, we evaluated it, and it is shipped. It's in DuckDB today in the 0.5 release. I'm very proud of that personally. All the thesis goals. And that is my talk. Thank you so much.